this is number 71. Title is Equidistant Chords. So we've had the word equidistant a few times before. What does equidistant mean? Yeah?
Equal distance.
Equal distance, perfect. So same distance would be another way to say it. So, and a chord, of course, is a line that connects 2 points on a circle. So here's a chord. All right, so in a circle, or congruent circles, so we're going to show the picture on just one circle, but it also would happen if you had two congruent circles. So in a circle or congruent circle, if two chords are equidistant from the center, if two chords are equidistant from the center. So here's the center of the circle. And of course, if I'm going to travel from the center of the circle to the chord, I don't want to go on an indirect route. I wouldn't go this way to get to the chord. I wouldn't go that way to get to the chord. The best way would be to go there. So if you make a perpendicular, then that's the straightest distance, the shortest distance. Okay, so that's the distance. That line I just drew is the distance from the center of the circle to the chord. So, but this is talking about two chords that are the same distance from the center. So in order to show that, I need another chord. And then another distance. And the situation is that these two chords are the same distance. So that is equal to that. So that's the situation. We have two chords that are the same distance from the center of the circle. If two chords are equidistant from the center. All right, so in that situation, what happens is then the chords are congruent. So if I put some letters over here, A, B, C, and D, then what's happening is chord AB is congruent to chord CD. And then we also know from another day that when you have a diameter that's perpendicular to a chord, it bisects the chord. So I'm just reminding you about a fact from another day. If I drew in this diameter, since it's perpendicular, then it cuts that chord in half. All right, then one more in a circle or congruent circles. If two chords are congruent, in a circle or in congruent circles, if two chords are congruent, So let me draw that situation. Here's our circle. And we have two chords. And they're the same length, they're congruent. So maybe this one is 12 inches and that one's also 12 inches. So I'll put a tick mark here and here, because that's the situation. This time we're starting off with knowing that the chords were congruent. Last time we found out that they were congruent. That was the result. Then the chords were congruent. But this time it's the beginning information, it's the given information that the chords are congruent. So if two chords are congruent, then what happens when you know that is then they are equidistant from the center. So here's the center of the circle. And the result is apparently this distance is equal to that distance. Since those chords are congruent. See, if this chord was longer, then it would be closer to the center, right? So it wouldn't be equidistant. But if the chords are the same length, then this distance is going to equal that distance. So the result is that that distance equals that. Last time we knew that the distances were equal up front. And then we found out, oh, well, that means the chords are congruent. But now we're flipping that around and we're saying, okay, if the chords are congruent, then the distances are equal. All right, that's it for the note card. Title today is Arcs and Chords 2. And we're going to start off with number 1. You don't have to draw this picture. We'll just all look at it and try to figure out what's going on. In this picture, there's 3 equal chords. And this distance here is, this measure is 120. So they're telling us this is 120 degrees, the measure of the curve. And they want to know what the measure of NP is. So we have 3 equal chords, and we want to know what the measure of that is. All right, so how many degrees is it all the way around? Yeah, 360 degrees all the way around the circle. And 120 of it is getting used up here. So if I take 360 minus 120, then that'll tell me this degrees. Okay, so from here to here, it's 120. So from here, the other way around, is 240. Because it's 360 all the way around. Okay, then these 3 arcs are equal to each other. Because when the chords are equal, the arcs are also equal. So this arc equals that arc equals that arc. So I could just take the 240 and divide it by 3 to figure out how big each is. Yeah.
Isn't it 80?
Yeah, good. So this comes out to 80 degrees. That's what we were looking for, the measure of NP. So this is 80, and this is 80, and this is 80. And the reason they're all 80 is because then it adds up to 360. All right, next we're going to go to number 7. And here's the picture on number 7. From C to D is a chord, and from A to B is a chord. And the information says that those chords are congruent. So this chord is congruent to that chord. And then there is this marked. So that's the distance from the center to the chord. And then there's also this marked. And that's the distance from the center to that chord. So if we know, they told us that AB is congruent to CD. Well, let me write that down. That's part of the given information. AB is congruent to CD. So then what do we know about these distances? Yeah.
It's equidistant.
They're equidistant. Good. So since they told us the chords are equal, that means these distances are equal. So then they have an expression for this. It's 3n minus 2. And they have an expression for this. It's n squared minus 6. So since the distances are equal, we can set n squared minus 6 equal to 3n minus 2. So the idea here is they told us the chords were congruent. And so based on that, we know that the chords are equidistant from the center. And then since they're equidistant, that means this number is going to equal that number. That's why we could put an equal sign in between them. Okay, so this is a little bit tricky to solve because it's got both an n squared and an n in it. And whenever you have that type of an equation, you need to get 0 on this side. So I'm going to subtract the 3n over. So it'll be n squared minus 3n. And then I'm also going to add the 2 over. So you take negative 6 plus 2, and you get negative 4. So I got rid of everything on the right side and put it over there on the left side, and that's why I have 0 over here. So anytime you have both n squared and n, that's how you start. You get 0 over here. And then after that, you have a couple of options. You can do quadratic formula, or you can factor it out. So you put it, if you do factoring, you put an n there and an n there. And then my strong advice is focus on the negative 4 first. Do we want numbers to multiply to be negative 4, or do we want them to add to be negative 4? Yeah, you want them to multiply to be negative 4. So just try to think about one thing at a time. We're going to try to find two numbers that multiply to be negative 4. Yeah.
Negative 1 and 3.
Nope. Negative 1 times 3 is negative 3.
And then there's negative 2.
So we're looking for two numbers that multiply to be negative 4. You tried negative.
Negative 3 and negative 1 and then negative. No.
That's okay.
Negative 1 and then negative 4.
Close. That's even closer. Because if it was negative 1 times negative 4, that would be positive 4.
So it's negative 1 and negative 4.
That would work also, yes. Okay, so there's two options, right? Negative 1 times 4 is negative 4, and 1 times negative 4 is also negative 4. There's a third option. Yeah, Jude.
Negative 2, positive 2.
Good. All right, so there's all the options for multiplying to be negative 4. And I was trying to get that because I want these two numbers to multiply to be that. Okay, then, since there's just one n squared here, we want the numbers to add to be negative 3. So there's the option we want, because that adds up to negative 3. So you put minus 4 and plus 1. And then you go from there. You set n minus 4 equal to 0, and also n plus 1 equal to 0. So in this problem, you get two answers, 4 and negative 1. Okay, moving forward to number 8. There's two chords. They're not telling us if they're equal this time, though. Last time they said they were equal. This time they appear to be equal, but we're not certain yet. Okay, then the distance from the center to this chord is marked as 7. And the distance from this to the chord is also marked as 7. So these two chords are the same distance from the center. So what does that tell us about the chords? Yeah, Manny. They're congruent. Good. So we didn't know at first whether the chords were congruent, but since these distances are equal, that means the chords are congruent. All right, then there's some stuff marked here. This is marked as 3x minus 3. That's the whole chord. And then this part of the chord is marked as x plus 3. So we know that this chord is equal to that chord, but we have a little bit of work to do to figure out what they are. Okay, so remember, if you have a diameter that's perpendicular to a chord, this is from another day, it cuts the chord in half. It bisects the chord. So that means if this is x plus 3, this is also x plus 3. So they told us this was x plus 3, but we can figure out that this is also x plus 3 because the chord is getting bisected. And then, since these are equidistant, we can set this equal to this. So x plus 3 plus the other x plus 3 equals the 3x minus 3. Is everybody doing okay with that? All right, so all of this adds up to 2x plus 6. And then you subtract 2x to the other side. And then you add 3 to the other side. All right, number 10, we have some information. It says a chord is 20 inches long. And then also it is 24 inches from the center of the circle. So a chord is 20 inches long, and also it is 24 inches from the center of the circle. So I'm going to circle around, try to draw this picture. And then we'll figure out this question. So try to draw the picture that goes with this situation. I wasn't trying to be funny when I said I'll circle around. That's a hint. There's going to be a circle in the picture. right, everybody's doing pretty good. Here's the circle. Then there's a chord. It's 20 inches long. And then the chord is 24 inches from the center of the circle. So here's the center of the circle. The distance is 24. And we went the shortest possible distance, right? So that means that's 90. And when you have a diameter that's perpendicular to a chord, what does it do? Yeah, bisects the chord. So that 20 just got cut in half, right? So now we could label this as 10 and that as 10. Okay, then the question's asking for the radius length. So you could draw the radius in anywhere, right? This radius is equal to that radius, is equal to that one. But the smartest radius to draw in would be this one, because then you would end up with a triangle. So totally fine to draw this radius, but then you don't end up with a triangle. So that's why I'm drawing that radius instead. And I'm going to label that R, because that's what we're looking for, the length of the radius. And then not only do you end up with a triangle here, but you end up with a right triangle. So there's lots of formulas that'll go with that. Pythagorean theorem, sine, cosine, tangent, all of that will go with this triangle. So you can do 10 squared plus 24 squared equals R squared. And then you just go from there. 10 squared is 100, 24 squared is 576. Just a comment about this equation here. Why didn't I move the 676 over and then try to factor it? It's got an R squared, right? Like over here, when I had n squared, I wanted to get 0, right? What was different about this equation versus this one? Yeah, Jennifer?
That one also had just the ring.
That one also had a regular n, right? This one doesn't have a regular r. So you only have to do all the fancy stuff when you have r squared and r. But here it's just r squared. So how do you get rid of the square? You square root. So since it just had r squared, we could solve it by square rooting instead of doing all that fancy stuff we did on number 7.